Welcome, everybody. Thank you for joining in. We are joined by Gilles Legault. He is with CB Supplies. We'll be doing a presentation. He will be doing a presentation on optimizing energy performance, hydronic heating systems, and the role of buffer tanks. So, Gilles, I'm going to let you take over. Thank you very much for joining us.
Well, thank you, Lee. It's a definite pleasure to be with a great group of people. Listen, we're going to be looking at an item that has been around for ages. I mean, if you think of buffer tanks, they were available back in even in the 20th century, believe it or not. But they're getting to be more and more important because of the role that it actually plays in our systems. So this is what I'm going to be talking to you about. We're going to be looking at different things, but again, for the people that don't already know me, Gilles Legault, I'm been around for ages, always in the industry, loving it. It's my passion. I'm a certified hydronic designer. As Lee was saying, I work for CB Supplies as a troubleshooter for them, also, technical support, and also doing a lot of design for them also. So, and a lot of teaching. I've been teaching the MCA in Alberta, but also teaching the CMMTQ in Quebec. So I'm staying very much involved also with different organizations such as CIPH. So even though my hair is getting gray, I think my heart is still very young and still keeping up to date with this beautiful industry. So we're going to be talking about buffer tanks, and the different things that we're going to be touching on are what are the benefits of buffer tanks, and what about a bit of history behind all of this. Like you were saying, Jill, they've been around for a while, but they're getting more and more important. So we'll get into the specifics such as stratification within buffer tanks, the amount of thermal energy that we can store in buffer tanks, the sizing of them. It's very important depending on the heating source that we're going to be using. We're going to have to size them differently. We'll also, at the very end, look at piping strategies. How should we do the piping around these buffer tanks, and end it all with just a brief overlook at some of these new systems and examples of systems where buffer tanks are really well positioned within all the components in the systems. All right, so let's have a look. There's two major benefits to a buffer tank. One of them being the hydraulic separation. We all know that that is very important, and even more so as we're getting into systems that have less fluid. So hydraulic separation is very important. And possibly the other great benefit is it will prevent our boilers or whatever heating source we have to not cycle. For the people that were in the previous session, actually Bob, not Bob, but anyways, Mr. Barba, maybe that's the way I should be calling him, John Barba. John was talking of, let's make sure we don't cycle those boilers too much, because there could be damage created and things like that. So that's the other great advantage. And in doing that, it will also permit us to have systems where there's many zones. And we know that is one of the evolution of our systems right now. We're getting into, even in commercial, we're getting into numerous zones where we used to have in the past 2-3 zones at the most. Now we're looking at multitude of zones. And at the same time, these zones are quite different in sizes. So we need some way of making sure that we're maximizing our efficiency in all of this. So again, the buffer tank is going to help us in all of that. It can also, at one point, help us to accumulate energy during some downtimes or during a period of time where energy cost is a little higher. So we want to, benefit from that and put energy somewhere so that we can use it when the energy costs are a little higher. We're going to be running into that very frequently in the next few years with all the EVs out there, the electrical vehicles that will all be plugged in at 6 o'clock in the evening. And you can imagine the draw that it's going to have on electricity. Well, we're going to need more and more ways of trying to spread that energy, or at least not have big draws on our systems. So, buffer tanks are going to be able to help us with that also. There's different things also that we can do. We can have coils within the buffer tanks so that if ever we're dealing with two different fluids, domestic hot water, let's say, and heating fluid, well, those are two different things. And we don't want them to mix. So we can also do that with buffer tanks. And we can also add some heating elements sometimes in buffer tanks too, as a backup. So a lot of advantages. And, in my mind, this is where the industry is going. And this is what we should be thinking in all of our systems. I'm showing you a simple system right now on your screen, and you can see a buffer tank that is piped, and you can see that it's actually doing a hydraulic separation between the boiler and the heating system, or the heating elements in the system. So it's doing that hydraulic separation, and at the same time, it's going to make sure that with the energy that we can store in these buffer tanks, it's going to make sure that ModCon boiler that I'm showing here will not be cycling too often, or we're going to try to make sure that we can control the cycling of the heating sources, right? So a bit about the history. Well, this picture speaks for itself. If we go back to we think that's a long way off now, but the 20th century, that's not that many years ago. But back in the 60s, the 50s, we used to have systems that were fed by gravity. So you needed to have a lot of fluid. Your boilers are similar to the one shown on the right here, great big boilers. But they, everything worked fine, except that we were not as efficient. We were not able to control zones as easily as we can, especially now that we've moved to very smaller heating sources, such as the one that we're seeing on the left. I think there's a question from the group, Lee. Sorry.
No, you're okay. I had to figure out how to get myself back on stage. No worries. Okay, yes, we have a question from the audience, guys. So we have a question. So are buffer tanks mainly for commercial and industrial applications?
Any application. The ideal place that you want to have a buffer tank is where there's going to be multiple zones. And, if residential, you've got multiple zones. And like I was saying, now that we're getting into some new technologies and that, we're seeing the same thing now developing in commercial. Small commercial, even larger commercial, although larger commercials, the systems are a little different. But, the small to medium commercial projects, we're now zoning. It's not just one zone. Even the smallest one, you'll have one zone for the warehouse and one zone for the offices. And you want to control those two separately. to make sure that your employees are comfortable in both the warehouse and your offices. And you can imagine also that the zones are going to be so much different as far as size. Your office might need only 2 GPMs, while your warehouse might need 20 GPMs. So these are things that you want to be able to control better, and a buffer tank will be able to do that. So all instances, anywhere where you've got a lot of zones, that's the perfect spot for buffer tanks. So getting back to,
we actually got one more question. We're gonna answer the questions and then I can run away again. So we have another one. So Brad said, I get generous sizing of common piping, but doesn't under 2 feet per second require special consideration about air entrainment?
It does. It does. And you know, Brad is touching on a very critical item that I've seen develop over the last 5 years or so. We're getting back to parallel piping, and because of that, hydraulic separation has become extremely important. And one way of getting that hydraulic separation is through properly sizing not only all of your components, but your piping also. And Brad, again, touched on a very important thing. If you want to have good hydraulic separation, your velocity has to be below 2 feet per second. In that case, your pressure is going to be lower, so you're going to have a good hydraulic separation. The problem, as again Brad is referring to, is that you're going to have difficulty in entraining air. So whenever you do hydraulic separation, you have to have a means of making sure that your micro bubbles, when your system is stopped, that micro bubble by gravity will find a way to an automatic air vent. If not, you will have air problems. So Brad is correct. Was there something else?
Yes, we got another one. So another question we have is, do buffer tanks reduce wear and tear on the system?
Good question. Exactly the other way around. It's you know, a buffer tank will relieve the boiler most definitely, because that boiler will not be cycling, will not be coming on and off frequently. So that buffer tank, it's got no mechanical parts per se in the buffer tank. So there's nothing that can go wrong with a buffer tank. It's just a tank. That's all it is. So, and yes, it does prevent cycling. So at the same time, it's going to help the circulators. It's going to help the heat source, all of that. So yeah, again, a good point. Good point.
All right, thanks, Gilles. I think we're good to go. That's all the questions. I'm gonna jump away and you're good to go. Keep going.
All right. Okay, so let's get going. Yes. So again, you know, we're going from systems that used to have a lot of water in them to systems that have much less water and smaller heat sources and all. So we have to take that into consideration. Actually, what we're also getting into, you know, we're reducing the side of fluid, but now we've got systems on which we can have radiant floors, we can have radiators, we can have fan coils, we can have, you name it. There's a number of items. And the other thing is that we're also getting more and more involved in heat pumps. So putting all of that together, we want to have systems that could be supplied by fluid at less than 120 degrees Fahrenheit. Not more than that. And if I can quote John Siegenthaler, for the people that know John, you know, just lately, I would say about a couple of years ago, started to say, guys, let's do all of our systems with supply temperatures less than 120 degrees Fahrenheit. Otherwise, we will not be able to service all this new technology coming on board in 5 years' time from now, let alone 15 years down the road. So let's do all of our systems now and make sure that our supply temperatures are 120 degrees Fahrenheit or less. Okay, so again, if we're in that mood of coming back at very low temperatures, nothing better than a buffer tank to help us achieve those goals. Okay, so a buffer, and we'll get into more specifics of that. But before getting into the specifics, one of the beauties of having a buffer tank is the stratification. Water by gravity, warmer water is lighter, so it's going to find its way to the top, and colder water is going to be at the bottom. So actually in our buffer tanks, we're going to have stratification. We're going to have different levels of water temperatures. The amount of energy which is going to be found in that buffer tank, even if I have this stratification, would be the same as if I had a buffer tank where all the water would be mixed. In other words, what you're seeing on the screen right now is a buffer tank. The one on the right, it's a blended, so everything is mixed. So it's got an average temperature of 110 degrees Fahrenheit. While the other one on the left has the very same thing. The average temperature, if you look at it, is going to be 110 degrees Fahrenheit also. But by being able to do a stratification and having hotter water at the top, it permits us to have a supply temperature at a higher level that can meet actually some of the zones that I have in my system. So stratification is a good thing. You would not want to have a buffer tank that would be horizontal. You want to have a buffer tank that is vertical, and the longer it is, the better, because the more stratification you can actually get through the buffer tank. So what about how much energy can I put in a buffer tank? That's a question that I very often get, and it's all based on the specifics of water and its density. Here's a table that you can get off the web, and it gives you the two things. Well, it gives you three things, but the two things that are very important is the weight of water, or you could have things like this also for glycol, but if it's water, you're going to have, let's say at 60 degrees Fahrenheit, water at 60 degrees Fahrenheit is going to weigh 62.37 pounds per cubic foot. Or you can also say that at 60 degrees Fahrenheit, you're going to have 8.3378 pounds per US gallon. Okay, so everything is based on that. It's the amount of energy that you can actually put in the water. So if I have a buffer tank, which is 80 gallons, let's say, well, 80 gallons of water, how much does that weigh? If you do the math, you will see it actually weighs 668 pounds, okay? And if I have a stratification within that buffer tank of 70 degrees, let's say I've got 160 at the top of my buffer tank and 90 degrees Fahrenheit at the bottom, I've got 70 degrees of stratification, or 70 degrees of energy within there. So 70 degrees times 668 pounds will give me 46,760 BTUs. So imagine in a buffer tank, which is considered a small buffer tank of 80 gallons, well, medium, I would say, if we're looking at the residential to small commercial, that's medium sized. You can actually put as much energy as you're going to need in a normal medium-sized home, enough energy in there to service your house for 1 hour. That 46,000 BTUs. That's a lot of energy that you can put in those buffer tanks. Now, Again, with that in mind, let's look at sizing them, okay? And you will see the logic behind trying to size a buffer tank and trying to work with the benefits that it gives us. And if you look at the formula, and again, you know, that's a common formula that you see everywhere. You want to know the volume. Well, the volume is equal to the cycle time. The T that you're seeing here, that's the cycle time. And in the industry, you know, we like to feel that when our boiler comes on, it's going to work for at least 10 minutes. Because otherwise, if it's less than that, it won't be as efficient, because a boiler, before it actually reaches its maximum efficiency, it takes a bit of time. You know, maybe 10 minutes is a little long, but it, you know, if we can work this to be 10 minutes, we get the maximum efficiency of our boiler. It actually goes to its maximum efficiency. If it's less than 10 minutes, you know, that boiler might be, this is when we say your boiler is cycling. When its cycle is less than 10 minutes, it's actually cycling, so never reaching its full efficiency. So the 10 is the time, the 10 minutes is very important. That's within the formula. And the uppercase Q, that's the size of your boiler. So let's say in my example, I've got a boiler that can produce 100,000 BTUs. And the lowercase q, well, that's the smallest zone that I have in my system. Or it could be the turn down cycle of my boiler, but it's the smallest amount of energy that I want my boiler to be giving me. So let's say that is 2,000, and all of that, of course, I'm going to be dividing that by 500 times the delta T. The delta T being the stratification, again, the difference between the top of the boiler and the bottom. So let's have a look at a very common case here. So let's say if you look at the numbers at the bottom where I'm pointing, well, if I have a cycle of 10 minutes, okay, I will want to multiply that by the difference between the capacity of the boiler, 100,000 BTUs, less my smallest zone, which would be 2,000 BTUs. So that works out to 98,000. And all of that, I want to divide it by 500 times the delta T. Okay, and if my delta T is 20, I've got 120 at the top of my buffer tank and 100 at the bottom. Well, I've got a delta T of 20 of stratification. So I do the math and I come out to 9.8 gallons. That would be the minimum. Now, I don't know any wholesaler that carries a buffer tank of 9.8 gallons. Usually it's a bit more than that. It's 30 or 40 gallons. But as you can see, I would need the minimum, a minimum of 9.8 gallons for my buffer tank. Now, like I said, the buffer tank is important for different things. And one of them is making sure that I'm coming back to my heat source at the lowest possible temperature. Because all of our new technologies, this is what we're aiming for. Okay, we're aiming to come back at the lowest temperature possible. Again, this is why John Siegenthaler keeps on telling us, hey guys, come back at minimum of 120. Okay, if you're coming back at 120, then you're future-proofing your system. While if you're not doing that, you're going to have problems. And if I look at a modulating condensing boiler, well, yeah, you know, when we talk of condensing, the more I come back at a low temperature, the more my boiler is going to be condensing. So in other words, the more latent energy it's going to be able to get out of the flue gases and put back in my system instead of throwing them out the chimney. So I'm going to be condensing on my first exchanger. giving some heat, doing some preheating to the fluid, so that when it gets into the second exchanger, it's already at a certain level. I only have to push it up by so many lesser degrees, let's say, to get back to my system, which, let's say, I have to supply at 120 degrees Fahrenheit. So as you can see, the lower my temperature is back to my modulating condensing boiler, it's going to be its efficiency is going to be increasing. The lower I'm coming back, the bigger efficiency I'm going to have. So, but you know, Brad probably could pick up on this because he seems really keen on hydraulic separation. Here's two ways of doing hydraulic separation with a modulating condensing boiler. It could be with other heat source, but if we're looking right now at modulating condensing boilers, you can either do it with a buffer tank, which in my mind is the best way, or you can also do it very efficiently. Well, maybe not efficiently, but you can do it, and you know that separation is going to be there with twin T's. Okay, double T's or closely spaced T's, you can do it. The only problem with closely spaced T's versus a buffer tank, you're going to get that hydraulic separation. But let's say you're modulating condensing boiler, which requires 8 GPMs. Okay, if it requires 8, and it requires 8 GPMs, that's the specification of the manufacturer. Otherwise, it's going to reset itself. It will never work properly. So if I have, let's say, 8 GPMs in my boiler loop, and I've got, for instance, let's say 4 GPMs in my heating loops. Okay, I've got actually 5 zones here, and let's say I only need 4 GPMs in those. Well, what is going to happen? Actually, some of the heated 120 degrees Fahrenheit water that's being fed to my heating system is going to come back in that closely spaced T, because it's doing the hydraulic separation. Okay, so it's going to be coming back, and if it's coming back at a higher temperature. Well, if I have a buffer tank, I'm doing that hydraulic separation, but I'm going to make sure that the bottom water is the one coming back to my modulating condensing boiler. And if I sized it properly and I've got 20 degrees of stratification in there, well, I will always be at the lowest temperature, which I cannot do with a closely spaced T. So this is why, you know, I've got a tendency, maybe I'm biased, but, you know, I've got a tendency of going to buffer tanks instead of closely spaced Ts. The other heating sources that we're seeing more and more of, and you know, we think of heat pumps, either air to water or water to water. Water to water has been around for a long time. Air to water also, but there's so much more development on the air to water side presently that you know, that's where the industry is going. But these systems, again, if I'm coming back at a lower temperature, the COP, the coefficient of performance of these heat pumps will increase tremendously. In other words, if I'm coming back at, let's say, 140 degrees Fahrenheit, I might get a COP, coefficient of performance, of 3, let's say. Well, if I'm coming back at a lower temperature, maybe 120 or even 100 degrees Fahrenheit, well, that COP is going to increase. So the performance increases. Again, you know, a good reason why we should have a buffer tank in there, making sure that my return temperature to the heating source is at its lowest, that we can have it. It's also the very same thing with solar. This morning, I was hearing on the news that we're starting to possibly think of doing things like the Germans are doing right now, where the solar systems are very common. We hear that our radiation or the sun has the same impact in Canada that it has in Germany. And Germany has increased an awful lot on the solar side. But again, if you're using solar, the lower you come back to your system, to your solar panels, the greater its COP is going to be. So again, let's make sure that we come back at the lowest temperatures when we get into these systems. So, but we have to be careful. We have to be careful. We don't want to oversize, especially when you're in solar. If we oversize our buffer tanks, then it becomes more difficult to get that upper high temperature, or the temperature that we want to be supplying our systems, to the point where, again, as an industry standard, when we're dealing with solar, we're going to say, well, the amount of how to size them. Well, you would want to have in the size of your buffer. You would want to have it at least a minimum of 1 gallon of storage for every square foot of solar collector, and a maximum of 3, because if that buffer tank is too large, then, like I said, it could become difficult to get that upper temperature to the level that you want to have it matching the system. We've got another 15 minutes, so did we have any other questions, Lee, or everything is fine? Okay. One of the other things that we're seeing more and more of, and that's more in the commercial. Well, we're seeing some in residential, but it's more in commercial. It's these renewable energy biomass boilers. Well, believe it or not, even those boilers, because their efficiency is so low and it takes them so long to develop the energy, that again, if we can come back at a very low temperature, its efficiency is going to be increased tremendously. So as you can see, pretty much everything. The only heating source that you should be careful with low temperatures is one that cannot condense. Everything else on the market that we're using right now, you've got to come back at a very low temperature. So let's use these buffer tanks. And how should we pipe them? Well, the simplest way is what you're seeing on the screen right now. It's what we call the 4-pipe buffer tank configuration. So you've got 4 pipes. So you're feeding on one side, you're feeding the buffer tank, and you're releasing the energy on the other side. Lee, there was a question?
Yes, we got another question. So Tasha is asking, why aren't more systems have buffer tanks? If they are truly more efficient, why aren't they everywhere?
Not a question. I mean, that's a statement in itself, Pascal. I mean, in my mind, every system should have at least every new system, the systems that where you've got heat pumps, where you've got condensing boilers, all of the ones that we've been talking about, they should have a buffer tank. In my mind, they're not expensive. They actually, you can actually put an air vent on them. You can also put a means of cleaning the magnetite that you have in your systems at the bottom with elements that will drag this magnetite to the bottom of the tank. So it's got so many benefits that it should be in every system, Pascal. This is the way I see it. Was that it, Lee?
That's it.
Okay. So that's the 4-pipe configuration. There can also be a 2-pipe configuration. And the beauty behind this is, as you can see, I can bypass the buffer tank. And why would I want to do that? Well, let's say my system is in demand. My system is asking for energy right now. It's in demand. And my buffer tank is also asking for a demand. So instead of going through the buffer tank, why couldn't I go directly to my system when both are in demand? So a two-pipe situation I'll be able to do that with a two-pipe situation or strategy. But the problem with this, you have to make sure that the piece of pipe which is going into your buffer tank is properly sized. You need hydraulic separation. You've got two circulators. Remember, hydraulic separation as immediately when you see two circulators in the same system, make sure they're hydraulically separated. Okay, so you need a properly sized pipe. It doesn't have to be long, but especially if your takeoff to the system is close to the buffer tank where it should be. Okay, that piece of pipe has to be sized at what, Bard? You were saying 2 feet per second. You're right. That's what it should be. Okay. Question, Lee?
Yeah, we got two. Oh, wait.
Okay.
Now I'm on stage. We have two questions. So one from Jacob: would a low loss header be considered a buffer tank?
Not really. Okay, it's not large enough to be considered. It will have some of the features that a buffer tank has. It will have the hydraulic separation. This is why we call it a hydraulic separator. There are also the possibility of putting a air vent on the top and also a strainer at the bottom to clean your system. So it's a beautiful item, but it's not for the purpose of making sure that you're not cycling your heat source and that you're really coming back at the lowest possible temperature. You need something a little larger than a hydraulic separator. I'm not saying a hydraulic separator is not good. I'm just saying it's not as convenient or as efficient as a buffer tank. Yeah, of course they cost a little less than a buffer tank. It's the same type of principle, but you can't put in enough gallons to be able to do some of the things that I talked about. With the cycling, making sure that a cycle is less than 10 minutes. It's more difficult to do in larger systems. So you need buffer tanks, and you need also, for hydraulic separation, you need buffer tanks, and you need low loss headers, a place where your velocity is going to be less than 2 feet per second.
Right. We had one more question.
Oh, yeah. You had two.
One from Mike. Go ahead. So are indoor-outdoor reset controls impacted positively or negatively with the use of buffer tanks?
It's, listen, a great question. I mean, that question, let me put up a slide here that I was not showing. Where's my... There we go. Have a look at this. When we want to do let's get out of hydraulic separation. When we want to do indoor-outdoor reset control, and we've got a buffer tank, well, where is the best spot to put that indoor-outdoor reset control? It's actually on the buffer tank. You can have one on the heat source. That is not a problem. But the best spot would be on the buffer tank. This is where the upper portion of your buffer tank has to be at a temperature that your system is going to be needing. Let's say it needs 120 degrees on design day. Well, you will want to have 120 degrees Fahrenheit at the top of your buffer tank. As the temperature outside increases, well, you don't need that 120 degrees anymore at the top of your buffer tank. It might be 110, could be 100, depending on the temperature outside. This is what indoor-outdoor reset control is all about. So as the temperature is increasing outside, you want to make sure that by keeping the same stratification, but you want the top portion of your buffer tank to be at a lower temperature, to be at the most efficient stage, to put it that way. So I would prefer putting the indoor-outdoor reset control on the buffer tank. instead of anywhere else in the system. Doesn't mean that you don't want to put it in other spots in your system, but basically the first spot that you should be thinking of is the buffer tank if you're thinking of indoor-outdoor reset control. Hopefully that explained that question.
Awesome.
Let's finish off on, unless there's other questions, Lee? No? Okay.
Nope, you're good. I'm going to hide again.
All right. Okay. So there we go. Now, the other thing that is important when I've got a 2-pipe buffer tank configuration is making sure that the flow is always in the right direction. You can imagine in some, fluid will want to go will want to take the easiest route, I should say, sorry, the easiest route. Well, it's there could be some back flows or whatever. So we want to make sure that in the part which is for the power source or the heat source, we want to make sure that there are in both, on the back end and on the front end, you want to make sure that you've got backflow preventers or check valves, I should say. Okay, that would be the proper word. Because of that, I prefer, and the industry is starting to prefer going to a 3-pipe configuration. But before we get in that, imagine the logistics of what's happening. Let's say again, my power source needs 8 GPMs. If you don't want that modulating condensing boiler not cycling, but resetting itself, stopping, then you've got to make sure that you put those 8 GPMs or 6 GPMs, depending on the manufacturer's specification, in there. So you could be circulating in that boiler loop or that those pipes going into your buffer tank at a higher velocity or more GPMs, I would say, than you are in your system. So what happens actually if it's 8 GPMs, 4 goes to the system and 4 goes to the buffer tank. All right. So you're actually heating the system with its highest temperature, and at the same time you're building up energy within your buffer tank. So great scenario. But like I say, make sure that there's no backflow in any of your system. This is why if you go to a 3-pipe configuration, you will not have that problem. You will have the advantage of feeding your system either from the buffer tank or directly from your heat source, your heat pump for the condensing boiler or whatever. So, and when you come back, you're not actually, you still need to do hydraulic separation. As you can see here, the piece of pipe that is coming out of my buffer tank has to be oversized. It has to be sized for 2 feet per second. Okay, so as you return, you're not having that problem of possibly having that flow go into the boiler piping. Okay, so good one to think about, the 3-pipe strategy. Okay, the 3-pipe buffer tank strategy. Now, another thing that I want to touch on is if we've got heat pumps, one of the beauties with heat pumps is that you can do hot water or cold water. So you can actually, use a buffer tank and reverse the stratification in your buffer tank during the summer months, and use that water for an air handler that is going to be cooling your house, or a radiant floor that is going to be cooling your floors if it's commercial. So you've got that possibility where in the past we could not do that. Us in hydronics, with the systems that we had, they were difficult. You needed 2 different systems for heating and cooling. Now with these heat pumps, you can do both. But you've got to reverse the flow of your buffer tank. So, or reverse the stratification of your buffer tank. So in the summer, should start with the winter. In the winter, you've got the hot water at the top and the cold water at the bottom, like we've just explained. So you've got a four-way diverter valve here that will either send the fluid to the top of your buffer tank or to the bottom, depending if you're winter or summer. Okay. So, and that is electronically controlled or just electrically controlled. So it just switches from one direction to the other. So in the summer months, in the winter months, you've got that hot water going to the top. And in the winter, in the summer months, now you just reverse that four-way valve, and you've got your stratification exactly the opposite way around. You've got the cold water at the bottom, and whatever is hotter is going to find its way at the top. Okay, and so you're going to be drawing from the bottom instead of drawing from the top when you're in the summer months. So in the summer months, again, on the other side of your buffer tank, you're going to have these diverter valves, depending on the season that you're in. So again, you're going to be diverting the flow, whether it's hot water that you want or whether it's cold water to an air handler, right? Let's have a brief look now. We're getting towards the end. So let's have a brief look at some examples. And go right ahead, fellas. Now we've got ample time, so any questions that you have, you can also at the same time ask them. Actually, there's one before we get into that, Lee. Yes.
All right. So Caitlin's asking, so can we incorporate domestic hot water production to a buffer?
Oh, a good question. Really good question. Absolutely. We didn't. I didn't think that we would have time to look at that. But let me bring up again another slide that will look at this. Where's my slide? Two of them actually. Look at this one. I've got a buffer tank. But of course, I've got two different fluids now. I've got domestic hot water and I've got heating water. So I've got, again, a two-pipe type of piping strategy. But within the buffer tank, I'm going to be putting a coil, which is going to do my exchange between the energy that I've got in the buffer tank and use that energy for domestic hot water. Different ways of doing it. Of course, I can have, in this case, I probably would want to have a buffer tank, which would be filled at 180 degrees Fahrenheit, or at least 160 degrees Fahrenheit. So possibly a little more than what my heating system, my heating elements are going to be needing. So you can see here where I'm showing you, there should be a mixing valve. If my buffer tank is at 160 or 180, well, I'm going to have to mix that down when I'm going to be drawing from the buffer tank to make sure that it's not too much for the heating side. So that's one way of doing it. But I've got an even better way. Have a look at this one. Using instantaneous water heaters. We know instantaneous water heaters are not as convenient for us because our supply temperatures from the municipality is sometimes a little too cold, especially when we get into the northern portion of our provinces. That water can have a tendency of coming down. Well, why couldn't we do preheating on an instantaneous water heater? So through an exchanger here, I'm taking whatever energy I've got in my buffer tank and I'm transferring it to this instantaneous water heater, preheating the water that's coming into the instantaneous water heater and giving me as much hot water as I want for a fraction of the cost that it would cost me if I had an electric water heater or a natural gas water heater. So good question. So it's very easy. Actually, if I had a heat pump also, I could have a means of recuperating the energy that my compressor is giving me in the in my heat pump, and using that energy to do some preheating on my domestic hot water. So, you know, a lot of ways of doing such things. Good. Let's get back to my
You,
examples.
you
Unless
actually
there's,
have one more question if you have time.
yep, yep.
All
Oh
right.
yeah.
So
We still have what, 10 minutes?
we got 8 minutes and 40 seconds.
All right.
So the question was, do you have an opinion on the Thermo 2000 TurboMax?
Beauty. It's a beautiful product. Of course, it's based on electricity. So this is why it's more common in Quebec. You won't see it as much in other provinces because of the cost of energy. I'm not saying that it's not something that should not be used in the other provinces. It's just that people are looking more at the, you know, when electricity in Ontario is 24 cents per kilowatt hour, and it's 7 cents in Quebec. You can understand that Quebecers are more attuned to using electricity than the people from Ontario. So, yeah, but it's a beautiful product because everything is pretty much like I've just shown. It's elements within a buffer tank, more or less, and it's giving me heating. It's giving me domestic hot water. So all done through electricity, actually.
Okay, we actually have one more question that's popped up too.
Sure.
So
sure.
Would the benefits of the efficiency of a buffer tank outpace the higher cost it takes to install? In layman's terms,
Absolutely.
would the general user actually benefit from having this installed? Would they save money?
Absolutely. Yeah, you know, you look at the cost of a buffer tank, I mean, it's minimal. Unless it's a great big one for commercial projects where you need the ASME specification. But, you know, if it's for smaller projects, these buffer tanks, I mean, what is it? It's a cylinder. It's a steel cylinder. It's got nothing to it. So they're cheap, and you can, depending on your system, you can see the advantages that you're going to be getting. Any one of your heat sources is going to be highly more efficient. If we come back to the modulating condensing boiler, you know, if I come back at 130 degrees to my modulating condensing boiler, my efficiency is going to be about 85%. So whatever energy I put in it, as far as natural gas is concerned, well, I'm going to get only 85% of what that gas can give me. But if I come back at, let's say, 80 degrees Fahrenheit, and that is possible with some of the systems that we now design. If I come back at 80, well, my efficiency is going to be very close to 98%. So all of the energy that I'm putting in there is almost all of it is going back to is going into my heating system. So highly efficient, and you know, to the point where you're going to be reducing your cost in that 1 year just by the amount, if you're using natural gas, just by about 10%. If you look at the math behind it, just about anybody could figure out that anywhere between 10 to 12% is going to be the economy if I can come back at a very low temperature. Well, 10% of normal house is what, $1,500, $2,000? Well, figure that out. I mean, that pays for the buffer tank in what? Less than 16 months, you know? So it's a highly efficient item to have in your system. Even more so if I'm with a heat pump. A heat pump without a buffer tank, you know, I might get a COP of 2. While with a buffer tank, that COP is going to be going to 4. So for every energy, you know, unit of energy that I put in, that electrical energy, because it's a heat pump, I'm going to get 4 times that amount of energy going back to my system. So again, I mean, it only makes sense. So that's where we should definitely be going.
We do have one
Listen,
question. Did you want to go back to your presentation? We can always
no.
We can get some of these
Okay,
questions answered after.
Listen, I'll quickly go into the two examples that I want to show, and that should give us a bit more time for some other questions.
Wonderful.
So,
thank you.
Okay, so let's have a look. This is a very simple type of installation. It's with now a conventional boiler, one that needs that should not be condensing. So I can actually do my buffering with that type of a boiler, and that boiler, if it has a two-way or three-way diverter valve, again, can also do domestic hot water, as you can see, through an exchanger within a hot water tank. Okay. And it serves also all of the zones in a two-pipe strategy. Now, here's the last one that I want to show you. It's or maybe there could be another one, but this one speaks for itself. It's what everybody sees right now in systems. You've got a modulating condensing boiler, buffering into a buffer tank. This buffer tank is not well displayed. It should be longer, my feeling, okay? And the buffer tank is supplying panel radiators at a certain temperature, could be 120 degrees, and will also service a radiant floor, which could be at 100 degrees Fahrenheit. So, of course, I would need to do a mix from that water coming out of the buffer tank that is sized for the panel radiators. So I would mix it down for my radiant floors. And at the same time, I could have an indirect hot water tank for my domestic on a priority demand. So whenever I need hot water, then my modulating condensing boiler will only look at the domestic water for a certain amount of minutes and then switch back to the heating after. So beautiful type of system. This is the systems that I think all of us right now in the industry, if we want to keep our edge, we've always had an edge in the industry. If we want to keep that edge, these are some of the systems that we should be proposing to our customers. Okay. Last one, very similar to what I've just shown you, but with a heat pump. Heat pump through a water-to-water geothermal type of installation. So very similar. Again, the beauty here is that I can do heating and cooling through an air handler.